Welcome back, everyone. Ready for another deep dive?
Absolutely. Always excited to dig into some fascinating material.
Today, we're taking a look at excerpts from Donald Knuth's The Art of Computer Programming. It's a classic.
Oh, absolutely. A seminal work in computer science.
And what we have are excerpts covering a really wide range of topics, from theoretical concepts to practical algorithms, even some brain-teasing puzzles in there.
I think what's so fantastic about Knuth's work is how he weaves those seemingly disparate ideas together. It really makes you think deeply about computation beyond just, the code itself.
Yeah, and one of the things that jumped out at me right away was how Knuth uses probability to tackle a real-world problem, like predicting how many chicks will hatch from a hen laying an eggs,
Wow.
each with its own specific hatching probability.
Right, and that's where something called the Poisson distribution comes in. It's a tool we use in probability to model the likelihood of a certain number of events happening over a specific time period. So, in this case, how many chicks hatch over, say, a week, given those probabilities for each egg.
So it's not just about the total number of eggs, it's about the chance of each one actually hatching. That makes it much more interesting than just simple multiplication.
Oh, for sure. And Knuth actually takes it even further. He asks, what set of probability distributions would make having a low number of hatched chicks the most likely outcome? It's like, how can we arrange those probabilities to minimize the chances of a ton of chicks hatching? It's a really fascinating exploration of how theoretical probability can be applied in practical scenarios.
That's such a great illustration of how these abstract mathematical concepts can be applied to real-world problems. But kind of switching gears a bit, we also encounter the classic n queens problem. I'm sure you're familiar with this one. How do you place 8 queens on a chessboard so that none of them can attack each other?
Yeah, a classic. And it's a perfect example of how backtracking can be used to solve problems efficiently. Knuth visualizes this process as a search tree, where each branch represents a decision point like where to place a queen.
So you're essentially trying different arrangements, backing up when you hit a dead end, like if a queen is under attack. I can definitely see how this is way more efficient than randomly trying out every single combination.
Precisely. And to optimize this process, Knuth cleverly uses data structures like arrays. So by representing the chessboard as an array, we can instantly test if a position is valid. If a queen placed there would be under attack without having to individually check every other queen on the board.
It's like a cheat sheet to tell you immediately if a move is allowed or not, which must speed things up significantly. Really highlights how even these seemingly simple choices about how you represent information can impact efficiency. Okay, but this next part blew my mind. Knuth uses bits of pi to estimate the number of ways a king can move from one corner of a chessboard to the opposite corner without revisiting any square. How on earth?
Right. It's brilliant. This is a great example of how he connects seemingly unrelated concepts. Essentially, we can use random sampling with pi's digits to generate a bunch of potential paths for the king and then analyze their properties. This lets us estimate the total number of paths without having to map out each and every single possibility.
Amazing. And what stood out to me was this concept of a path's profile. Instead of getting bogged down in the details of each specific path, Kuthi focuses on key characteristics, like how many moves it takes or if it crosses the center of the board.
Exactly. And by analyzing those profiles, we can actually uncover statistical properties about the entire set of possible paths, like the average path length or the likelihood of certain patterns emerging. It's a really cool way to get deeper insights into the problem without getting lost in the specifics.
And he even mentions this technique called ZDDs, which we'll probably encounter later in the book, that can give us the exact answer. I'm already intrigued. But before we jump ahead, there's this little puzzle that caught my eye, a word search, but with a mathematical twist.
Oh, yeah. It looks simple on the surface, but this puzzle is actually an introduction to a concept called color-controlled covering, which Knuth delves into later. It's basically a technique for finding arrangements that satisfy certain constraints, and this word search serves as a fun way to introduce the idea.
So it's like a mental warm-up before tackling the heavier stuff. I love how Kuth incorporates these lighter moments to keep things engaging. Now, speaking of heavier stuff, the next part of our dive takes us into the world of Boolean satisfiability. This is where logic and computation really intersect. We're basically trying to figure out an unknown Boolean function based on just its output for specific inputs, like cracking a secret code.
It's a fascinating problem, and Knuth shows us how we can represent this as a set of logical clauses, each one representing a constraint on the function's behavior.
It involves introducing variables to represent the presence or absence of specific terms in the function's formula. It's a bit like piecing together clues to reconstruct, say, a crime scene.
Precisely. The idea is to encode the problem in a way that lets us use these powerful algorithms specifically designed for solving Boolean satisfiability problems. And these algorithms systematically explore different possible solutions, figuring out if they meet the given constraints.
And this is where algorithm L enters the picture, right? This is a specialized algorithm designed for tackling these SAT problems. I'm curious to see how this one works in practice.
Algorithm L is what we call a clause learning algorithm. It essentially tries out different assignments of values to those variables in our logical clauses. It's almost like trying different combinations on a lock until you find the one that opens it.
But algorithm L is much more sophisticated than just brute force guessing, right?
Oh, absolutely.
Right.
It uses some really clever techniques to narrow down the search space and find a solution efficiently. And to make things even faster, Knuth introduces this idea of redundant clauses. These are clauses that don't actually add any new information, and by identifying and removing them, we can speed up the algorithm significantly.
It's like decluttering your workspace to focus on the essentials. I can see how that would make a big difference. But speaking of efficiency, what really struck me throughout this dive is how Knuth emphasizes the importance of carefully crafting algorithms and data structures.
Absolutely. He demonstrates time and again that elegance and efficiency go hand in hand. He shows us how thoughtful design choices can lead to algorithms that are both incredibly powerful and beautifully simple.
Yeah, it's like a master craftsman carefully shaping their tools to create a work of art. It's this attention to detail that makes Snoot's work so influential. Now, you mentioned earlier how algorithm B is well suited for the n-queens problem because we can test properties quickly, but how exactly do we achieve that super fast testing?
Well, that's where choosing the right data structure becomes crucial. Kuth highlights how using arrays specifically for the n-queens problem can significantly speed up those property tests.
So instead of going through a whole list of comparisons for every possible queen placement, we can use arrays to instantly check if a specific column, diagonal, or row is already occupied. It's like having a map that instantly tells you which territories are already claimed.
Exactly. The way we structure the information plays a huge role in how quickly we can access and process it. Knuth's insights into data structures show just how crucial it is to represent information thoughtfully within a computer.
And speaking of representing information, I love how Inuth uses bits of pi for random sampling to estimate the number of king's paths on a chessboard.
What's fascinating is how he connects this idea of randomness to the challenge of counting those paths. By generating random paths and looking at their characteristics, we get a good estimate of the total number of paths without having to painstakingly map out every single one.
It's like taking a random sample of a population to understand the overall demographics. Except here, our population is all the possible paths, and the demographics are things like the average path length or whether it passes through certain squares.
And to make that analysis even more insightful, Knuth introduces the idea of a path's profile. It's basically a compact way to represent its essential features, allowing us to study those statistical properties across all possible paths.
It's like boiling down a complex entity to its defining traits. Instead of getting lost in the details of each individual path, we can focus on broader trends across all of them.
Exactly. This abstract view helps us move beyond simple counting to uncover those deeper statistical properties and gain a much richer understanding of the problem.
Now, remember that word search puzzle we mentioned, the one with a hidden mathematical message? Well, it turns out that's just the tip of the iceberg when it comes to color-controlled covering.
Right. Knuth uses that seemingly simple puzzle as a gateway to a much broader concept. Color-controlled covering is this powerful technique for solving a wide variety of combinatorial problems where you're trying to find arrangements that meet specific constraints.
So it's not just about finding words in a grid. It's a general framework for problems where you need to assign colors or labels to objects in a way that follows specific rules.
Absolutely. The word search just serves as a concrete example of this much broader concept. By starting with that concrete example, Knuth prepares us to tackle more complex applications of color-controlled covering later on.
It's like using training wheels before you hop on a bike. He gradually introduces us to more and more challenging concepts, building on our understanding step by step. But before we delve deeper into color-controlled covering, we're taken back into the world of Boolean logic, with the challenge of figuring out an unknown Boolean function. It's like trying to decipher a secret code based on just a few glimpses of its output.
And this problem really highlights the power of logical reasoning to uncover those hidden patterns. Knuth demonstrates this really systematic approach By taking the information we have and encoding it as these logical clauses. Each clause represents a constraint on the unknown function.
And he does this by introducing variables that represent whether or not certain terms are present in the function's formula. It's like meticulously piecing together those clues to reconstruct, to say, a crime scene.
Exactly. The goal is to use the available information to figure out the structure of that unknown function. By carefully constructing those logical clauses, Knuth transforms the problem into something that we can then tackle with algorithmic solutions.
And that's where algorithm L comes in, right?
Mm.
A powerful tool for cracking those logical puzzles.
Yes. Algorithm Hell is designed specifically for these Boolean satisfiability problems. It systematically explores different ways to assign values to those variables and sees if those clauses can all be satisfied simultaneously.
It's a bit like trying different key combinations on a lock until you find the one that unlocks it.
Sure.
But I imagine algorithm L is much smarter than just randomly trying every single combination.
Oh, you're absolutely right. It uses some sophisticated techniques to navigate that search space efficiently and zero in on a solution. What's really neat is that it learns from its mistakes. Whenever it runs into a conflict where the assignments it's trying violate those clauses, it analyzes that conflict and adds a new clause to avoid making the same mistake again.
So it's constantly refining its strategy based on what it learns. That's incredibly clever. And then, to boost its efficiency even further, Knuth introduces the concept of redundant clauses.
Redundant clauses are the ones that don't actually add any new information to the problem. By getting rid of them, we can significantly speed up the algorithm.
It's like decluttering your mental workspace to focus on the most essential elements. Even in the realm of logic, a little tidying up can make a big difference.
This ties back to Knuth's overarching emphasis on optimizing our algorithms and data structures, whether it's by choosing the best way to represent information or by eliminating unnecessary computations.
It's about working smarter, not harder.
Exactly. And it's a principle that goes beyond computer science. It's a valuable lesson for any field where we aim to solve problems in the most effective and efficient way possible.
And speaking of efficient solutions, remember how Knuth hinted at using ZDD technology to find that exact number of quarter-to-corner king's paths on the chessboard?
Ah, yes. ZDDs, or Zero Suppressed Decision Diagrams, are this really powerful data structure for working with sets. They exploit the structure inherent in a problem to create a really compact and efficient representation, which allows us to work with sets way faster than traditional methods.
So instead of listing out every single possible path, which would be a ridiculously long list, we can use ZDDs to represent that set of paths in a much more condensed, manageable way.
Precisely. And this compact representation makes it much easier to do things like count the total number of paths, find the shortest path, or even analyze statistical properties of those paths.
It's like having this super efficient filing system that lets you quickly locate and analyze the information you need.
And what's really cool is that ZDDs aren't just a theoretical concept. They actually have real-world applications in fields like model checking, circuit design, and even bioinformatics.
So they're not just a curiosity for solving chessboard puzzles.
Not at all. Their ability to represent and manipulate sets so efficiently makes them incredibly versatile. They're used to tackle a wide range of problems where sets and their properties are central.
Okay, ZDDs are definitely moving up on my list of things to learn more about. But before we dive into that, let's switch gears and talk about another classic problem: finding the shortest path in a graph. This may sound a bit abstract, but it has real-world applications everywhere, right?
Absolutely. It's relevant to everything from finding the best route on a map to optimizing data flow in a network.
So how do we actually go about finding those shortest paths?
Knuth discusses several algorithms designed for this, including Dijkstra's algorithm and the Bellman-Ford algorithm.
Those names ring a bell, but could you give us a quick refresher on how they work?
Both algorithms systematically explore the graph, starting from a designated source vertex. As they explore, they keep track of the distances from that source to every other vertex and update those distances as they discover new paths.
So it's like a wave spreading out from the source, gradually reaching all the other points in the graph.
That's a great way to visualize it. Now, Dijkstra's algorithm is particularly efficient for graphs where the edges have non-negative weights. It works by repeatedly selecting the vertex with the smallest known distance from the source and updating the distances to its neighbors.
So at each step, it picks the most promising path. That sounds a bit like a greedy approach, always choosing the option that seems best at that moment.
You're right, there are similarities to greedy algorithms, but the Bellman-Ford algorithm can handle graphs with negative edge weights, although it's generally slower than Dijkstra's algorithm.
So there's a trade-off between flexibility and efficiency. We need to choose the right algorithm based on the specific graph we're working with.
Precisely. Knuth's discussion of these algorithms highlights the importance of understanding those trade-offs in algorithm design. There's rarely a single best algorithm for all situations.
It's about picking the right tool for the job, considering factors like the size and structure of the graph, whether there are negative edge weights, and how crucial speed is.
Exactly. And that emphasizes the need for careful analysis and design in computer science. We need to understand the strengths and limitations of different approaches to make informed decisions.
It's not just about knowing how to solve a problem. It's about understanding why a particular solution is effective and what limitations might exist.
You've got it. This deeper understanding allows us to apply these techniques to new and even more complex problems.
One thing I find so fascinating about computer science is how it provides tools to model and solve problems from so many different disciplines.
Absolutely. Computer science has these powerful concepts that are applicable to fields ranging from physics and engineering to biology and economics.
It's like having a universal language for problem solving.
And Youth's work really embodies that interdisciplinary spirit. He connects those computer science concepts to ideas from other fields, showing us how algorithms and data structures can be applied to all sorts of problems, sometimes in really surprising ways.
We've already seen examples of this, like using probability distributions to understand those chick hatching patterns, or using random sampling with pi to estimate those king's paths on the chessboard.
Precisely. Those examples show how computational thinking can be applied to problems that might not seem computational at first glance.
It's about recognizing underlying patterns and structures that we can then model and analyze using computational tools. It's about thinking computationally, even when the problem itself doesn't explicitly involve computers.
And that ability to connect these seemingly unrelated ideas is really at the heart of what makes computer science so intellectually stimulating. It's about breaking down complex problems into smaller, more manageable pieces, and then using computational techniques to analyze and solve them.
Like putting together a jigsaw puzzle, piece by piece, until the full picture emerges. And just like a challenging puzzle, the process can be both demanding and incredibly rewarding.
Absolutely. Computer science is all about embracing those challenges and finding creative solutions to those complex problems.
And one of the biggest challenges in computer science is managing the increasing complexity of the systems we build.
You're absolutely right. As those systems become more sophisticated, we need new techniques to handle that complexity, and Knuth actually discusses several approaches. A key concept here is abstraction.
Abstraction is all about hiding unnecessary details and focusing on the essential features of a system, right? It allows us to build these complex systems by layering simpler components on top of each other.
Exactly. Think of building a skyscraper. You don't need to know the intricate details of every beam and bolt to design the building as a whole.
Right, you can abstract away those lower-level details and focus on the overall design of each floor and how they connect to each other.
Precisely. And by doing that, you manage that complexity and make it more understandable and maintainable. Abstraction is a fundamental principle in computer science, and it allows us to create powerful but manageable software systems.
It's like finding that balance between detail and simplicity. Concealing the complexity behind these well-defined interfaces, we can concentrate on the core interactions between those components.
And that ability to manage complexity is crucial in a world where software systems are becoming increasingly interconnected and sophisticated.
And speaking of interconnectedness, that brings us to networks, which are the backbone of modern computing.
Networks enable communication and data sharing between devices worldwide. Knuth discusses different aspects of networking, including routing algorithms, those data transmission protocols, and of course, network security.
Could you remind us what each of those does?
Of course, routing algorithms determine the optimal paths for data packets to travel through a network. Data transmission protocols ensure reliable and efficient communication between devices, and network security measures are there to protect sensitive information from unauthorized access.
So it's a whole ecosystem of algorithms, protocols, and security mechanisms working together to ensure information flows smoothly and securely.
Precisely. Knuth's exploration of networking highlights just how important it is to understand how all those different pieces work together.
It's like understanding the flow of traffic in a city. We need to know the layout of the roads, how those traffic signals operate, and the measures in place to ensure safety and efficiency.
And just like in a city, managing that flow of data in a network is crucial for everything to run smoothly.
One of the big challenges in networking is ensuring that data is reliable, even when errors happen. Data can get corrupted during transmission due to various factors, like noise on the line or hardware failures.
That's where error detection and correction techniques come in to play a crucial role in guaranteeing the integrity of that data.
It's like having a proofreader for data. They detect and correct those errors to ensure that the information reaches its destination intact.
Exactly. Error detection and correction are vital for reliable communication, especially in applications where accuracy is paramount, like financial transactions, medical records, or scientific data.
In those cases, even a single bit error could have serious consequences.
You're absolutely right. Those applications demand robust error handling to maintain data integrity.
Knuth's discussion of error detection and correction techniques really highlights the importance of redundancy and using clever encoding schemes, right?
Yes. Redundancy essentially means adding extra information to the data, which allows us to detect and correct errors. And those encoding schemes ensure that the data is represented in a way that minimizes the impact of any errors that do occur.
It's like having a backup plan for your data, adding that extra layer of protection to make communication more resilient to those inevitable errors.
And that resilience is critical in a world where data travels vast distances over diverse networks.
Now, shifting gears to security, protecting sensitive information from unauthorized access is becoming more and more vital in our interconnected world.
Absolutely. Knuth discusses several aspects of network security, including encryption, authentication, and access control.
I'm familiar with those terms, but could you remind us how they all work together to keep data safe?
Sure. Encryption scrambles the data into an unreadable format, making it gibberish to anyone without the secret key to decrypt it. Authentication is all about verifying the identity of users or devices to ensure that only authorized parties can access sensitive information. And access control mechanisms restrict access to specific resources, preventing unauthorized users from tampering with data or disrupting the system's operations.
So it's like a multi-layered defense system protecting that data from multiple angles.
Exactly. And Knuth emphasizes a holistic approach to security, considering not just the technical safeguards, but also the human factors.
So it's not just about building strong walls and locks. It's also about educating users on best practices and creating policies and procedures that minimize risks.
You got it. Truly secure networks require both those robust technical measures and a vigilant user community.
It's a shared responsibility where everyone plays a role in protecting sensitive information.
Exactly. And Knuth's discussion of those security principles gives us a foundation for understanding the complexity of the challenge and for developing those effective strategies to mitigate the risks.
Now, taking a step back to consider the bigger picture, it's clear that computer science is constantly evolving. New technologies and paradigms emerge all the time, pushing the boundaries of what's possible.
It's a field that never stands still. And what's remarkable about Knuth's work is that while it's rooted in these fundamental principles, it anticipates many of the advancements we've seen in recent decades.
His discussions of data structures and algorithms have really laid the groundwork for all those sophisticated software systems that we use every day, from operating systems and databases to machine learning algorithms and artificial intelligence.
You're absolutely right. His focus on efficiency and elegance has influenced generations of computer scientists, shaping the way we design and build these software systems.
And his exploration of networking and security really foreshadowed the challenges and opportunities of this interconnected world that we live in today.
Absolutely. His work gives us this foundation for understanding and tackling the complex issues that come up in a world where data constantly flows across networks and security is absolutely paramount.
So while Knuth's work can seem theoretical and abstract at times, it's deeply connected to the real world and the challenges we face in this digital age.
Exactly. His insights into algorithms, data structures, networking, and security are more relevant than ever. They provide a framework for understanding and solving the complex problems that shape our world.
It's a real testament to the enduring power of fundamental principles and the importance of clear, elegant thinking in computer science.
Absolutely. Knuth's work remains this timeless classic, continuing to inspire and inform generations of computer scientists and engineers.
Now, remember how Knuth teased the idea of ZDDs, those zero-suppressed decision diagrams? They sound incredibly powerful for working with sets.
They really are. ZDDs offer a remarkably compact and efficient way to represent sets, capitalizing on the problem's inherent structure to minimize storage space and computation time.
It's like having a super efficient filing system for sets, where only the absolutely essential information is stored, eliminating all that unnecessary redundancy.
Precisely. This compact representation allows us to perform operations on sets much faster than traditional methods. For example, we can count the elements in a set, check if one set is a subset of another, or even do set operations like union, intersection, and difference with incredible efficiency.
So it's not just about saving space, it's about making computations on those sets lightning fast.
Absolutely. And that speed is what makes them so valuable for a wide range of applications, like model checking, circuit design, and bioinformatics. They're a real game changer for solving problems where sets and their properties are central.
What's interesting is that ZDDs didn't really gain widespread recognition until relatively recently. It reminds us that computer science is full of new discoveries, even in areas that seem well established.
Absolutely. Computer science is constantly evolving, with new ideas and techniques emerging all the time. ZDDs are a perfect example of how a seemingly theoretical concept can have a profound impact on practical applications.
It just reinforces the importance of staying open to new ideas and exploring unfamiliar territory. Who knows what other groundbreaking discoveries are waiting to be made?
Exactly. The future of computer science is full of possibilities, and I'm excited to see what innovations emerge in the years to come.
Now let's shift gears a bit and talk about another fascinating concept Knuth introduces: backtracking.
Backtracking is a fundamental technique in algorithm design used for a wide variety of problems, particularly those that involve searching for a solution within a vast space of possibilities.
It's like navigating a maze, trying different paths until you find your way out.
That's a great analogy. Backtracking is all about systematically exploring that search space, making choices at each step, and backing up when a choice leads to a dead end.
So it's a trial and error approach, but with a systematic and intelligent way of making those choices and retracing our steps.
Exactly. Knuth demonstrates the power of backtracking through various examples, including the classic n-queens problem.
Right, trying to place those 8 queens on a chessboard so that they can't attack each other. It's a puzzle that has captivated mathematicians and computer scientists for ages.
And backtracking provides this really elegant and efficient way to solve it. We start by placing a queen in the first row, then move to the second row, trying out different positions until we find one where the queen is safe from attack. We keep doing this row by row, backing up whenever we hit a conflict.
It's like playing a strategic game of chess, anticipating your opponent's moves and ensuring your queens are always protected.
Precisely. The beauty of backtracking is its ability to avoid exploring unnecessary paths. Whenever we run into a conflict, we know that any further choices along that path will also lead to conflicts, so we backtrack and try a different route.
It's like pruning a tree, removing branches that we know won't bear fruit.
Exactly. That pruning makes backtracking much more efficient than simply trying every single possibility, allowing us to tackle problems with a huge number of potential solutions.
And backtracking isn't limited to just the M-Queens puzzle.
Right. Not at all. It's applicable to a wide range of problems, including solving Sudoku puzzles, finding paths in mazes, and even generating all possible permutations of a set of elements.
So it's a really versatile technique that can be adapted to solve problems in various domains.
Absolutely. Knuth's discussion of backtracking really highlights its elegance and power, demonstrating its ability to solve complex problems in this systematic and efficient way.
It reminds us that sometimes the most elegant solutions are those that embrace trial and error, but do so with intelligence and foresight.
Precisely. Backtracking is a testament to the ingenuity of computer scientists in finding those clever ways to navigate vast SERP spaces and uncover solutions to those challenging problems.
Now let's shift our focus to a field that often captures the imagination: artificial intelligence.
Artificial intelligence, or AI, is all about creating intelligent agents, these systems that are capable of reasoning, learning, and acting autonomously.
It sounds like something straight out of science fiction,
Yeah.
but AI is becoming a reality at an incredible pace.
You're absolutely right. AI is transforming industries from healthcare and finance to transportation and entertainment.
And while Knuth's work may not directly address AI, It lays the groundwork for so many concepts and techniques used in modern AI systems.
You're right. His discussions of algorithms, data structures, and problem-solving strategies are essential for understanding how those AI systems operate.
For example, machine learning, a core area of AI, heavily relies on algorithms to analyze data, identify patterns, and make predictions.
Exactly. Machine learning algorithms are trained on these massive data sets, using statistical techniques to learn from that data and improve their performance over time.
It's like teaching a computer to learn from experience, much like we humans do.
In a way, yes. Machine learning lets computers learn from data and make decisions without being explicitly programmed for every single scenario.
And Knuth's work provides those building blocks for these sophisticated learning algorithms.
Absolutely. His insights into algorithm design, data representation, and problem solving are crucial for understanding how those machine learning systems are built and how they work.
So even though Knuth's work didn't explicitly talk about AI, his contributions have had a profound impact on the field.
Exactly. His work has laid the foundation for many of the concepts and techniques driving today's AI revolution.
Now let's explore another fascinating aspect of computer science, the relationship between hardware and software.
Hardware refers to the physical components of a computer system, like the processor, the memory, and those storage devices. Software, on the other hand, consists of those instructions that tell the hardware what to do.
It's like the brain and the body. The hardware provides those physical capabilities, while the software provides the intelligence and the direction.
That's a great analogy. Knuth emphasizes the importance of understanding both hardware and software to design truly efficient and effective computer systems.
His discussions of data structures and algorithms take into account the underlying hardware architecture, optimizing how that data is stored and processed for maximum performance.
Precisely. Understanding how the hardware works allows us to create software that takes full advantage of its capabilities and minimizes any bottlenecks.
It's like understanding the strengths and limitations of your tools.
Exactly. We need to choose the right data structures and algorithms based on the hardware we're working with.
And this interplay between hardware and software is becoming even more critical as we see the rise of specialized hardware architectures like GPUs and FPGAs.
Absolutely. Those specialized platforms offer incredible performance gains for certain types of computation, but they require software that's specifically designed to leverage their unique capabilities.
So it's a co-evolutionary process. Advancements in hardware drive innovation in software and vice versa.
Exactly. Knuth's work provides this foundation for understanding this intricate relationship between hardware and software, guiding us in designing systems that are both powerful and efficient.
Now let's talk about a crucial aspect of computer science that's always top of mind: security.
Security is absolutely paramount in today's digital world. Sensitive information is constantly flowing across networks and being stored on devices that are potentially vulnerable to attack.
It's like trying to fortify a castle in a world full of skilled invaders.
Knuth emphasizes this multi-layered approach to security, considering both the technical aspects and those all-important human factors.
So it's not just about building strong walls and locks. It's also about educating users about security best practices and creating policies and procedures that help minimize those risks.
Absolutely. A truly secure system needs robust technical safeguards, but it also needs a vigilant user community.
It's a shared responsibility, with everyone playing a role in protecting that sensitive information.
Precisely. And Knuth's discussion of security principles lays the groundwork for understanding this complex challenge and for developing those effective strategies to mitigate those risks.
Let's zoom out for a moment and consider the broader impact of computer science on society as a whole.
Computer science is transforming how we live, work, and interact with the world around us. It's driving innovation in nearly every industry, from healthcare and education to finance and transportation.
It's hard to imagine our lives without computers and the software that powers them.
Exactly. Computer science is everywhere, and its impact on society is profound and multifaceted.
And Knuth's work, while focused on the technical side of computer science, also reflects an awareness of these broader societal implications.
You're right. His writings emphasize clear and elegant thinking, rigorous analysis, and a deep understanding of the tools we use.
Those qualities are not just essential for computer scientists, but for anyone navigating the complexities of the modern world.
Absolutely. Knuth's work reminds us that computer science is about more than just writing code. It's about cultivating a mindset that values precision, efficiency, and creativity.
It's about finding elegant solutions to those complex problems and leveraging technology to make a positive impact on the world.
Exactly. And as computer science continues to evolve and shape our future, Knuth's principles and insights will continue to guide and inspire generations to come.
Now let's delve into another fascinating concept that Knuth introduces the idea of literate programming.
Literate programming is a philosophy of software development, and it really emphasizes writing code that's not just functional, but also readable and understandable by humans.
So it's not just about getting the computer to do what we want, it's about making the code itself a work of art, something that can be appreciated and understood by others.
Exactly. Knuth believes that code should be written more like literature, with this clear narrative structure and explanations that make those logic and design decisions really transparent.
It's like writing a novel, where we carefully craft the plot, develop those characters, and use language to convey those ideas in a really compelling way.
And just like a well-written novel, the goal of literate programming is to engage the reader, making that code not just functional, but also aesthetically pleasing and intellectually stimulating.
It's about elevating code from this purely technical artifact to a form of artistic expression.
In a way, yes. Literate programming acknowledges that code isn't just this set of instructions for a computer. It's a form of communication between humans, and it should be treated with that same care and attention to detail.
And what's interesting is that literate programming isn't just about making the code look pretty. There are practical benefits too, right?
Oh, absolutely. Code that's well written and well documented is much easier to understand, maintain, and modify. It reduces those chances of errors and makes collaboration on projects a lot smoother.
It's like investing in quality craftsmanship. It might take a bit more effort up front, but it pays off in the long run by making the software more robust, reliable, and sustainable.
Exactly. Literate programming really promotes clarity, elegance, and communication in software development.
And it's a philosophy that's had a big influence on many programmers and software engineers. It's led to tools and techniques that really promote those practices.
You're right. We have things like documentation generators, code formatters, and version control systems, all of which make it easier for programmers to write that code that's both functional and well documented.
So literate programming is not just some idealistic notion. It's a practical approach to software development with tangible benefits.
Absolutely. It's a reminder that computer science isn't solely about technical skills. It's about communication, collaboration, and really striving for excellence in our work.
Now let's talk about another fascinating aspect of computer science, the relationship between theory and practice.
Computer science is this beautiful blend of theoretical foundations and practical applications. The theory provides that intellectual framework, while practice drives innovation and pushes those limits of what's possible.
It's like two sides of the same coin. You can't really have one without the other.
Exactly. And Knuth's work is a prime example of this. His writings are deeply rooted in these mathematical principles and rigorous analysis, but they're also full of these practical insights, showing a deep understanding of real-world applications.
Like his discussions of algorithms and data structures, they're not just abstract mathematical concepts. They're tools for solving real problems and need to be designed with those practical considerations in mind.
Precisely. Knuth recognizes that algorithms aren't just theoretical entities, they're tools to solve real-world problems, and they have to be designed with those problems in mind.
So it's not enough to just prove that an algorithm works correctly in theory. We also need to think about things like efficiency, how much memory it uses, and how it performs on real-world data sets.
Absolutely. Knuth's work stresses the importance of bridging that gap between theory and practice, making sure that those theoretical insights actually translate into solutions that work in the real world.
It's about finding that balance between elegance and efficiency, where mathematical rigor meets that real-world impact.
Exactly. And that balance is what makes computer science such a dynamic and rewarding field to work in.
It's this constant interplay between the abstract and the concrete, the ideal and the real. And Knuth's work really captures that beautifully.
One thing that's so striking about Knuth's work is how seamlessly he blends these different areas of computer science. He doesn't see them as separate disciplines, but as interconnected parts of this larger whole.
We see this throughout his work. For instance, when he talks about algorithms, he often brings in concepts from data structures, probability, and even logic. It's like he's weaving this tapestry, connecting those different threads to create this rich and intricate pattern.
Precisely. This holistic approach is essential for understanding the complexity of computer science and coming up with those elegant, efficient solutions.
It's about seeing that bigger picture, understanding how all those different parts of a system fit together and how they influence each other.
And this systems thinking is becoming more and more important as our computer systems get more complex and interconnected.
We can't afford to just focus on one tiny piece of the puzzle. We have to consider the entire ecosystem and understand how changes in one part can ripple throughout the whole system.
Absolutely. Knuth's work really provides this framework for that systems thinking. He encourages us to step back from the immediate problem and consider that broader context.
And even though Knuth delves into these intricate details, he never loses sight of the bigger picture. He always brings us back to those fundamental principles and the overall goals.
You're exactly right. It's his ability to connect the dots to see the big picture while still appreciating those nuances of each individual element. That's what makes his work so insightful and so enduring.
It's a real testament to his brilliance as computer scientist
Hmm.
and also to his ability to communicate these complex ideas in a way that's clear and engaging.
As we start to wrap up our deep dive into the art of computer programming, a question that comes to mind is, we've explored all these fascinating algorithms, intricate data structures, and these mind-bending puzzles, but how does all of this actually translate to the real world?
That's a great question, and I'm sure many of our listeners are wondering the same thing. We've seen how Knuth's work underpins so many of those technologies that we use every day, from search engines and social media to our smartphones and even self-driving cars.
It's easy to take those technologies for granted, but behind each of them is this complex interplay of algorithms, data structures, and programming techniques. And Knuth masterfully explains these concepts.
He pulls back the curtain and lets us peek behind the scenes at the intricate workings that make our digital world possible. By doing so, he empowers us to be more than just passive users of technology. We can be active participants in its creation and its evolution.
Exactly. By understanding those fundamental principles of computer science, we can really appreciate the ingenuity of the systems that we use, envision new possibilities, and contribute to those future technologies.
It's like learning the language of innovation. Once we understand the grammar and vocabulary of computer science, we can start to write our own stories and create those innovative solutions to the challenges that we face.
That's the true legacy of Knuth's work. It's not just a collection of algorithms and data structures. It's this invitation to explore the power and beauty of computer science and use that knowledge to make a real difference in the world.
So, as we conclude this part of our deep dive, I encourage all of you listening to keep exploring, keep learning, and keep pushing the boundaries of what's possible. The world of computer science is vast and always expanding, full of wonders just waiting to be discovered.
Remember, even a journey of 1,000 miles starts with a single step. Take that first step, dive into the world of computer science, and let your curiosity be your guide.
You never know what incredible things you might create along the way.
Yeah, it's remarkable how all these different pieces that seem so separate actually come together to form this foundation of what we call computer science.
It really speaks to Knuth's ability to see that interconnectedness between all these concepts and how they build upon each other. It's not just algorithms in isolation, right? It's about how they work with data structures, how probability influences design, how logic underpins their correctness.
And that brings us back to something you touched on earlier, those ZDDs. They seem to pop up in all sorts of contexts, from counting paths on a chessboard to representing sets. I get that they're powerful, but I'll admit I'm still a little fuzzy on exactly how they work.
Okay, let's break that down a bit. ZDDs, or zero-suppressed decision diagrams, are essentially a really clever way to represent sets efficiently. Imagine you have a set of items, and you want to describe all the possible subsets of those items. A simple way would be to just list out every single subset, but that could get really big really fast.
Especially if you're starting with a lot of items in your original set. Exactly. ZDDs come in and give us this much more compact way to represent them by taking advantage of the relationships between those subsets. They use this branching structure, kind of like a decision tree, where each branch represents a decision point. It's like, do we include this particular item in the subset or not?
So instead of listing out every single combination, we're encoding the decision-making process, the path that leads to those combinations.
That's a great way to think about it. And the zero suppressed part comes from the fact that ZDDs are really good at handling sets that have a lot of zeros, meaning sets where a lot of the potential items aren't included. They do this by collapsing these redundant branches, which makes the whole representation much smaller.
So it's like one of those space-saving vacuum bags where you squeeze out all the air to fit more stuff in. We're squeezing out all the unnecessary information to represent the set compactly.
Precisely. And that compact representation is what makes ZDDs so powerful. It lets us perform operations on those sets, like union, intersection, and difference, much more efficiently than we could with a more straightforward representation.
So we're not just saving space, we're also speeding up calculations.
Exactly. And that speed boost makes them really valuable for a ton of applications, from model checking and circuit design to things like bioinformatics. They're a go-to tool for tackling problems where sets and their properties are front and center.
One thing that really jumps out from exploring Knuth's work is his constant emphasis on efficiency. It's not just about finding a solution, it's about finding the most elegant, most efficient solution possible.
He's a huge advocate for the idea that elegance and efficiency go hand in hand in computer science. And he demonstrates this through carefully chosen examples and these beautifully crafted algorithms.
It's like he's saying that well-written code is more than just getting the job done. It's about getting it done in a way that's both effective and beautiful, almost like a well-crafted piece of art.
And that attention to detail, that pursuit of elegance and efficiency, it sets a standard for the whole field. It encourages everyone to strive for not just functionality, but also clarity, conciseness, and beauty in their code.
It's a legacy that continues to inspire. Well, as we wrap up this deep dive into Knuth's The Art of Computer Programming, I want to thank you for taking us on this journey. It's been a fascinating exploration full of unexpected connections and thought-provoking ideas.
The pleasure was all mine. It's always a joy to delve into these topics with you.
And to all our listeners, we hope this deep dive has sparked your curiosity and given you a new appreciation for the beauty and power of computer science. It's a world full of wonder and possibility, so keep learning, keep experimenting, and who knows what amazing things you might discover.